And thank you for joining us for this first lecture video for chapter 4, where we start talking about, still we're talking about alkane molecules. Those are, as far as reactivity goes, you could say kind of a boring molecules in that they really lack functional groups, so they don't really do much of a reaction. But as in the future, we're gonna be seeing cycloalkanes with functional groups on them. So this is sort of in preparation for that, and we're gonna see different types of isomers, maybe starting in this chapter. And so, like, I first want to make sure that we're on the same page about that concept of isomers. And first, you might know this already, but the prefix iso in Greek means the same. And so isomers, fundamentally, they're kind of the same or similar compounds. They are the same in that they all share the same molecular formula. But the constitutional isomers have different constitutions or different connectivities, different structures altogether. Okay, so for instance, if you have the formula of C6H12, that could be cyclohexane, 6 carbons, or it could even be cyclobutane with 4 carbons with 2 branches sort of attached to it somewhere. Or you could even be a cyclopropane with just 3 carbons, but then you have 3 other carbons somewhere, right? And so cycloalkanes in general will have this formula. Notice that for linear alkanes it said +2, right? But because it's cyclized, it's lacking 2 extra hydrogens. And you might notice this even more explicitly if you actually try to make these molecules with your molecular model kit. If you try to, if you have a hexane, linear hexane, and then try to make cyclohexane from it, you'll notice you have to take 2 hydrogens from each end of the chain to make that connection to make it a cycle. And so we would say this is not saturated. Cycloalkanes are unsaturated molecules in the sense that they don't have the maximum number of hydrogens that you could have. Of course, the maximum would be when you have the linear molecules. Okay, and another way, so that's cycloalkanes. As far as constitutional isomers, these 3 are all constitutional isomers of one another, sharing the exact same formula. One way to think about these is that if you go from one constitutional isomer to another, you would have to sort of break your models. If you're using a molecular model kit, that's if you have to break it up and then combine them together to make the molecule, that's a constitutional isomer, as opposed to, remember, the conformational isomers or conformers, right? You just have to rotate around a single bond and you get to that structure. So those are not constitutional isomers. If you forget, please review chapter 2 notes for conformers or conformational isomers. We're gonna start seeing different stereoisomers, and that stereochemistry is gonna be important. And what we mean by stereoisomers is they not only share the same formula, but they actually share the exact same connectivities, but the 3D, something about the 3D arrangements is different. As an example, you might have this cyclohexane with 2 methyl groups pointing up, but if you compare that to this cyclohexane where one methyl group is up but the other is down, those would be examples of stereoisomers. Okay. You would still have to kind of, if you're going from this model to that with your molecular model, okay, you would have to take this methyl group off as well as the hydrogen on this carbon and swap them around. But otherwise the connectivities are the same. This carbon is still attached to a methyl group and this carbon is still attached to a methyl group. Okay, so hopefully that distinction makes sense to you. So these are like another way you would know these two. And in sort of this lecture video, we're not going to really spend much time talking about the nomenclature of cycloalkanes because they're really named and drawn similarly or the same way as alkanes. Linear alkanes we went over in the last chapter, but I'm sure we'll go through some practice problems for nomenclature in class, but certainly please practice those in the homework questions. And if you do, this structure on the left might be called cis 1,2-dimethyl cyclohexane. And based on the rules we've already gone over for linear alkanes, it might not be too surprising for you that it says 1,2-dimethyl cyclohexane. Now this cis indicates the stereochemistry because both of these two structures would be named 1,2-dimethyl cyclohexane. So the only distinction is whether the two methyl groups are on the same side or the opposite side. And so for that reason, the second structure would be essentially named the same, except that these two methyl groups are in the trans relationship. Trans in chemistry means like opposite of each other. Cis means the same or same side, usually referring to stereochemistry. Okay, so that's the only difference there. Maybe we'll underline here. Okay, so you would see those sort of prefix in a molecule name starting in this chapter. Okay, and kind of related to stereoisomers are the conformers. But remember the difference is these are actually really the same molecules, but rotated around single bonds. So they might seem it seems like the only difference between conformers might be the 3D arrangement. So you might get confused between conformers and stereoisomers. But stereoisomers, you do have to swap out two groups on a carbon and change the positions, 3D positions, to go from one isomer to the other. Okay, hopefully that makes sense as far as the distinction there. Now, let's actually start talking about the cycloalkanes. And starting in this chapter especially, it becomes really important for us to understand the 3D-ness of these molecules. I think we talked about the fact that it's important for you to know these molecules, they're actual 3D objects. And here's really why. In the last chapter, I think we talked about different types of strains. And as you can imagine, right, like cyclobutane, this would be a cyclobutane because it's a butane, but it's cyclic. This would experience two different types, well, maybe you could argue for three different types of strains. First, right, because this angle is 90 degrees, and so for that reason, this is much less than 109 degrees that sp3 carbon would like to be, remember that this carbon has two other hydrogens. It's an sp3 hybridized carbon, and so therefore there will be some angle strain, because this angle is much less than the ideal 109. Another type of strain that this would be experiencing would be the torsional strains. And remember, that's when the two bonds are eclipsed together, because remember, bonds are made of electrons. If they're eclipsed together, then they would experience some repulsion. Now, in real life, though, if you actually make the molecular model, you might be able to see this, but this molecule actually slightly puckers in a way. And so the actual structure actually looks somewhat like this. I'm a little bit exaggerating the puckeredness of this, but okay, so cyclobutane is a little bit puckered. Oops. So as to avoid the strains, especially the torsional strains. Okay. Maybe I didn't show that quite obviously in this drawing, so maybe I'll do that. Once it puckers like that, they're not exactly eclipsed, and really the only way to see this and tangibly hands-on would be for you to build your own molecular model, so please do so. And also, once it's puckered, it's a little bit different than 90 degrees. You might see at least some of the bond angles. Okay. I said you could argue for a third strain. When it's eclipsed like that, these two atoms are pretty close together, so there will be some steric strain as well. Okay. Now let's think about cyclopentane. If you know how to do geometry calculations pretty well, you might know that this angle in a pentagon is going to be 108 degrees. So there's actually a very little angle strain. So that's good. But there would still be some torsional strain if this molecule is flat. Right, then these hydrogens would eclipse. But once again, like in real life, if you form this molecule with a molecular model kit, you might notice that this is, again, the natural way to make this molecule would not be a flat molecule, but it would take a conformation that looks like this. It's often called the envelope conformation of the cyclopentane. And again, that's to avoid some strains. Okay. Now, what about the cyclohexanes? Well, these are, I would say, the most six-membered rings are 5 and 6-membered rings are most commonly seen ring sizes in organic chemistry. Cyclohexane you're going to see a lot. Okay. You might notice that if you do geometric calculations, which I don't require you to be able to do for our class, but this would be 120 degrees if it's a flat molecule, which is much bigger than 109. And so what that means is there would be an angle strain if this molecule was indeed flat. the key concepts being if this was flat, but you can guess probably by now that in real life this is actually not a flat molecule. Indeed, it has this type of a structure, and this is called a chair conformation, because it kind of looks like a lawn chair. Okay, and again, really the best way to learn this and see this for yourself would be to make the model yourself, and so please do. Okay, so one of the key concepts here, cyclohexane, it's definitely not flat. Okay, now this chair conformation is an interesting one because it can actually flip, and chair flip, and I don't mean like just flipping over a chair, but it's a conformational change through a series of single bond rotation, and that's an important distinction. So we do use this conventional term, chair flip, but I just want you to know it's not just a matter of flipping over a molecule like like a Jesus did at the temple with the tables or something. That's not what we mean by the chair flip. Flip has to do with a series of single bond rotations, and again, this is one of those things you can really get your hands on, experience, or see it for yourself if you make this with a model. And when a chair flip happens, and again, sorry, I don't know that I can explain this super well in a iPad video lecture, but I'm sure we'll demonstrate this in class in person. But even then, you would be looking at it from distance, so like just practice this with your own model kit. And what's going to happen is it goes through sort of an intermediate conformation called boat conformation, and then the chair flip completes like this. And the reason why this is important is once you put a substituent on these chairs, predicting which of these conformation that it prefers is going to be important to predict what the molecule wants to do. So this is a really important skill. Okay, and so for that reason we're going to put a lot of emphasis here. But if we keep track of these two carbons, okay, what we are saying about the chair flip is that these are the same carbons, so we can keep track of them. What's happening is in the chair flip, one end flips up through the rotation of these bonds, and then becomes the boat conformation, and then this side flips down through the rotation of these four bonds, and that's the conformation you get. It's kind of like if you think of this as a lawn chair, right? Like if you could just kind of imagine like somebody sitting there, like maybe that's not a very good picture of a person, but hopefully you can kind of see that this kind of looks like a lawn chair. One way to think about this change is that the footrest that would be like this part becomes the headrest. In this lawn chair, right? Like this was the footrest, now it becomes the headrest. This was the headrest now becomes the footrest. That's what we mean by chair flip. Okay, so we'll say this is a chair flip. Okay, and then I put some unequal equilibrium sign here because, as you can imagine, boat conformation experiences a much more strain, and you might not realize that as much if you just look at the drawing on paper, but if you make this molecule in real life, you'll notice that these two hydrogen atoms experience quite a bit of steric strain. And so for that reason, this boat conformation is not very stable. And so for that reason, this is kind of a high energy transition state that you have to go from one conformation to the other. But this chair flip does indeed happen fairly rapidly at room temperature. Okay. Now let's think about like how we might depict what's going on with these chair flips, and to do so we kind of need a new vocabulary words, and those are equatorial and axial groups. Because cyclohexane, right, each carbon has two hydrogens on this, and there's the up and downness to them, but we could draw this as like so. And when you draw in the hydrogens, you'll notice that there's some hydrogens that are going straight up and down. Like these guys. Okay. And then there are hydrogens that are kind of sticking out to the side, like these. And those are one type of hydrogens. Now, what we call axial are the ones that are up and down, like these 1, 2, 3, 4, 5, 6 axial protons. And then the equatorial protons are these, the rest of the protons or hydrogens that are kind of going to the side, almost horizontal, but not quite. Equatorial equator is like what's around the sphere. If you think of this as a sphere, like what the hydrogens around the equator sort of are the equatorial hydrogens, and the axial ones are the in parallel, the ones that are parallel to the axis. Okay. And when you draw this, I want you to notice how this bond is parallel to those two bonds, and this bond is parallel to that, this bond is parallel to that, this is parallel to this, this is parallel to that. So as long as you can find what each bond is supposed to be parallel to, you should be able to draw these pretty well. So these are the equatorial hydrogens because they're in equatorial positions. And then these guys are axial. Okay. Hope that makes sense. This axial and equatorial, one of the common mistakes I see among students is they confuse these with up and down. Notice that a given axial hydrogen could be pointing up or down, okay, and the given equatorial positions could be slightly up or slightly down. So axial and equatorial has nothing to do with up or down. And in fact, if this chair flips, I want you to notice how the maybe I'll use different colors to draw the hydrogen bonds. Okay, so the ones that were orange, you'll notice, becomes the axial protons after the chair flip. Okay. And then ones that were axial or green becomes equatorial after the chair flip. And again, this is one of those things you can only sort of see for yourself and make sense if you use your own molecular model kit. So please do. And maybe we'll say that the up and down that doesn't correspond axial versus equatorial. Okay, given proton goes from axial to equatorial depending on the chair flip, but they still remain either up or down. Notice, for example, this hydrogen is up in axial. After the chair flip, it becomes up in equatorial. So up protons stay up, down protons stay down. Like this is maybe it might be helpful for us to number this. So this could be carbon number 1, then this would be carbon number 1, this would be carbon number 4. Right, this hydrogen is equatorial and down in this conformation, chair conformation. Here in the after the chair flip, it's axial and down. Again, use your own molecular model kit to make sense of this. And earlier we said that all this chair flip and axial equatorial business becomes even more important when you have substituents on the cyclohexane. So here's one example, right? Here's methyl cyclohexane. Okay, in one conformation, this methyl group could be in this position, and once the chair flips, I hope it makes sense to you that the methyl group will be in that position, right? We would call this the equatorial conformer. Oops. And this would be the axial conformer, because the what single substituent was in the equatorial conformer, it's in the equatorial position, but in the axial conformer, it's in the axial position. Now, any guess as to which of these conformations might be preferred by the molecule or more stable? And again, if you are working with a molecular model kit, I bet you can guess correctly, because it becomes pretty evident that there's going to be this steric clash between the axial hydrogens and axial methyl group. In fact, you could probably almost touch one of the hydrogens of this methyl group with these hydrogens. There'd be a major steric hindrance. Oops. And we call this 1,3 diaxial interactions. Oops. And the reason for that is because this is, if this is carbon number 1, this would be 2, 3. So hydrogens at the 1, 3 positions in relationships are having these steric interactions, right? So because of that, this axial conformer is much less stable, and so for that reason, equilibrium lies far to the left, to the equatorial conformer. And then in fact, if you measure the energy level of these two conformations, the left structure or conformation is 1.7 kilocal per mole more stable. And these things tend to be additive. So if having a methyl group in the equatorial, it's beneficial by 1.7 kilocal per mole. If you have another one, a methyl group, there's like 3.4 kilocal or close to it per mole energy benefit and so forth. And these are for our class, especially, of course, I don't necessarily need you to remember some specifics like these numbers, but I want you to definitely be able to predict that this is the preferred conformation. Now, when you just have a single substituent, it's pretty easy, because whenever it's in the equatorial position, that's the more stable conformation. But if you have more than one substituent, right, or three even, then it gets a little bit more difficult. And so those are the examples we want to think about in the next video, and then more or so in our class time. So I'll see you then.